Alright, THS Chem Team, here's your next round of video notes, and this is going to be our introduction into reactions. And today we're going to look at the first two types of reactions, which are synthesis and decomposition reactions. These are the easier of the reactions that we're going to learn. You're going to write these down in your notebook on the pages provided by your teacher. Let's go ahead and take a look at these reactions and get started. Alright, so the first type of reaction is the simplest, and that is called a synthesis reaction. And so when we go through a synthesis reaction, we are going to produce one new substance. So in these synthesis reactions, typically we are going to take two elements and chemically combine them into one product. So the key that tells us that we have a synthesis reaction is that we have one product. There is no plus sign over here on the product side of our reaction. So if you look to the right of the arrow in a synthesis reaction, there will be no plus sign over here. There's just going to be one compound. Typically for our purposes here in our first chemistry class is that we're going to put a metal and a non-metal together to form an ionic compound. So that means when we go to finish or completely go through these reactions, we'd be able to predict what our products would be by looking at what metal and non-metal are put together and then crisscrossing our charges or oxidation states to figure out the formula for our product. Okay, so let's take a look at a couple examples. Alright, so the first one here, we have magnesium metal is being burned in the presence of oxygen. And so if we look at this, we are starting with two elements, a metal and a non-metal. So we know that if we are going to actually chemically combine those, we're going to produce an ionic compound. And in this case, our ionic compound is going to be magnesium oxide. So the way we're going to start this is we're going to write out our two ions that we know will be formed. So we have magnesium and oxygen. And we know that if we were to put these two together, just like we would do before, the metal always comes before the non-metal. We would look on our periodic table and we would find that magnesium has a charge of +2 and then oxygen has a charge of -2. And crisscross our charges, that would end up with a subscript of Mg2O2. But we know that when we have an ionic compound, we're always going to make this the simplest ratio as possible. So a 2 to 2 is actually the same thing as a 1 to 1. So whenever we see these equal but opposite charges, we're just going to push our substances together and drop the subscripts. So the formula we're actually going to have here is going to be MgO for magnesium oxide. Alright, so there's our products. But now we need to actually finish our reaction by balancing it. So now that we know that what we're going to produce when we react magnesium oxygen is magnesium oxide of MgO, we need to go through and balance our equation. And right away I see that oxygen has a subscript 2 on the reactant side and does not have a subscript over here on the product side, so that means 1. So I'm going to put a coefficient of 2 in front to give me 2 oxygens. When I do that, that also gives me 2 magnesiums. And so I have to come back over here to the reactant side and put a 2 in front of Mg to give me 2 magnesiums. So my balanced equation would be 2, 1, 2. Alright, so our second reaction, we're going to take sodium metal and react it with chlorine. Now it doesn't matter if it was chlorine plus sodium, because they're both elements. As long as they're on the left side or the reactant side of the equation, it's going to tell us that since we have two elements, the only thing we can do is combine them into a compound, which tells us it's a synthesis reaction. So we're going to figure out how to combine sodium and chlorine. If they bond, they're going to make sodium chloride. So that tells me I'm going to have Na will be first because that's the metal, Cl will be second because that's the non-metal, it's the positive and the negative, so positive is always first. And again, we're going to check our charges to make sure our formula is correct. So if we look at our charges, we find sodium on the table. It's an alkali metal, and it has a +1 oxidation state. And chlorine, a halogen, has a -1 charge. Again, these are equal but opposite charges, so the same magnitude with the opposite sign. We crisscross them. That means I would need, for my ratio, 1 sodium for every 1 chlorine. Alright, so we're going to lose the charges. We don't want to have the charges when we write our chemical formula because it should be balanced or neutral. Alright, so we know that our formula for sodium chloride is NaCl. And now the last thing, once you know your formula is correct and your products are correct, is to balance the equation. And again, right away I see that there's a 2 subscript here for chlorine and there's no subscript over here. So I'm going to multiply by 2 to give me 2 chlorines on the product side. When I do that, that also gives me 2 sodiums. So I have to come back over here to the reactant side and put a coefficient of a 2 in front of sodium. And I already have my chlorines taken care of, so this also balances as a 2, 1, 2 for my coefficients. So again, to identify this as a synthesis reaction, the key is that I see 2 elements chemically combining, so the only option I have is to form 1 compound as a product. So in your notebook, here are 2 examples I want you to write out and try and complete them and bring them to class. So pause this, take a second, write these down in your notebook. Alright, so on the next page, our second type of reaction is called a decomposition reaction. And you've seen this term before, probably in biology. So decompose means to break something down. It's the same idea in chemistry. So when we talk about a decomposition reaction, we're taking 1 reactant and we're going to break it into smaller pieces. And typically that means we're going to take a compound and split it into the elements that make it up. Typically this requires an input of energy, meaning these reactants are already bonded, so they're relatively stable. They don't want to be separated. So if it requires an input of energy, that means that most of the time these decomposition reactions are going to be considered endothermic reactions, meaning we have to add, it has to absorb energy in order for it to take place. So the key to identify this, just like it's the opposite of a synthesis reaction. The synthesis reaction, there is no plus sign on the product side. In a decomposition reaction, you only have the 1 reactant, so there is no plus sign on the reactant side. So let's take a look at a couple of these for some examples. These are typically easier to do than a synthesis reaction. Alright, so for number 1, we have mercury 2 oxide, and then you see our arrow, which means there's nothing else we can do over here on the reactant side besides to decompose or break it apart into what makes it up. So this mercury oxide has 2 elements in it. So when we write out our products, we're going to end up with mercury as one of them and oxygen as the other. Now this is where we can't just necessarily leave it as Hg plus O, because now we're going to look at whether we know if it's a monatomic element or a diatomic element. And so remember, our diatomics are those 7 elements that always come in pairs whenever they're by themselves. So since neither one of these are bonded to anybody, we have to know if any of them are diatomic. And mercury is definitely not one of our magic 7 that are diatomic, but oxygen is. So that means since it's diatomic, we're going to throw a subscript 2 to tell me that oxygen is coming in pairs when it is by itself in its elemental form. Okay, so decomposition reactions are relatively easy because all you have to worry about is whether or not it's going to be a monatomic or diatomic element once you have separate. So once you've split it apart or decomposed it into the 2 elements that make it up, and you know whether it's monatomic and diatomic and your formulas are correct or your symbols are correct on your product side, the last step, as always, is going to be to balance. So the balancing equations part is never going to go away. Alright, so again, let's see here. I see that I do not have a subscript for oxygen on my reactant side, so that means 1, and I do have a subscript on my product side of 2. So we'll put a 2 in front here to tell me that I have 2 oxygens. That also means I now have 2 mercuries. So I'm going to put a 2 in front of Hg here to balance the mercuries out, which means I'm left with a 1 if you want to put a 1 there for O2. Alright, next one. The next one is the decomposition of water. Now typically this is done with electrolysis, is the most common form to do this, and we talked about that earlier in the year. But if we were to take water and separate it or decompose it into the elements that make it up, it is made up of hydrogen and oxygen. Again, once you know the two elements that make it up, then go back to whether it's a monatomic or diatomic element. So remember to the 7 elements that are diatomic, and we look back and we know that hydrogen is part of that, so that means it definitely has to have a subscript 2. Oxygen we just did before, so we know that that is always going to have a subscript 2 whenever it is in elemental form, meaning not bonded to anybody. It wouldn't matter if you wrote oxygen plus hydrogen as long as they are to the product side of your reaction. So now that we know that we have the correct formula for our products, last step is to balance it. Alright, so I see I have 2 hydrogens on my reactant side and 2 hydrogens on my product side, so that is good. 1 oxygen on my reactant side, 2 oxygens on my product side, so I'm going to have to put a coefficient of 2 in front. When I do that, that gives me 4 hydrogens here. I have 2 there, so I'm going to put a coefficient of 2 in front of my hydrogen on my product side. So there's our finished balanced equation for the decomposition of water. And once again, here are 2 more examples that I'd like you to write in your notebook and finish the reaction and give them a try. Bring them to class, and please bring questions. Chem Squad out.